Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 2 on one-sample estimation. I'm going to scroll down from the course website down to the course notes, and we'll be looking at Chapter 2. I recommend, as always, downloading the R code that goes along with this lecture that's in the PDF file, and in the R link here you'll find all the code that appears in the chapter, and you can follow along running it in your R Studio console. So here's the PDF file. Estimation in one-sample problems. So a one-sample problem is when you draw from a population a single sample to estimate some quantities about that population. In the next chapter we'll be looking at two-sample problems where we take a sample from one population and a sample from another population and make comparisons. But in this case we're just making inference about a single population. We have some learning objectives, and my goal in this video is to jump through a little quicker than some of the other videos to shorten the time. So inference for a population mean. Suppose you've identified a population of interest where individuals are measured on a single quantitative characteristic such as height, weight, IQ, and you select a representative sample from that population, and then you want to make inference about parameters from that population. Typically we are interested in the mean, though sometimes we are interested in other values as well, such as the maximum or the median or some measure of variability like the standard deviation. But we're going to focus our attention on the population mean as the measure of central tendency. And so the basic setup here is we've got a light blue circle, which is the entire population. There's a huge set of values there potentially, and it's hard to measure everything. That's why the US only takes a census every 10 years. And so instead, because we can see very little, we draw a sample. And this sample is a subset of the population. And how we sample is very, very important. We want to draw a sample such that it is representative of the entire population. And one strategy for doing that is a simple random sample or some other random sample strategy where subsets of that same size, of size n, say we took a sample of size 30 observations, that every set of 30 observations had the same probability of being drawn. Once we collect that sample, this is what we actually observe, right? The population's unobserved, but we draw a sample from that, we observe the population, and then what we learn from the sample, we then make inference from what we learned back to the population. And the main quantities of interest here are going to be the mean and variance or standard deviation. And we know how to calculate the sample mean, which we'll call y bar. It's you add up all the values of y and divide by n. In sigma notation, that's the equation there. All right. So our two main methods here are going to be confidence intervals, which is about inference to the population, which means we don't know what the true population mean is in this scenario. Mu is the true population mean. We don't know what that value is, but from our sample, we can calculate y bar. There it is, y bar in the top right corner. And that is going to be our best guess for what the population mean is. And so that will be our inference for that. And our confidence interval sort of gives us a range for plausible values of that population mean, though the technical definition of a confidence interval is typically not what we care very much about. The other strategy we'll use is a hypothesis test. That's when we're interested in asking a question and having an answer. For example, is the population mean equal to 0? Then we will perform a test and either have enough evidence to reject that hypothesis that it equals 0 and conclude that it equals something else, or we will say that we have insufficient evidence to reject the hypothesis, the null hypothesis that we've stated, that it equals 0. And you can, of course, specify in your test that mu equals any possible value, just using 0 as an example. All right, so we need some definitions now. We've got something called the standard error, which is the standard deviation of a sampling distribution. All right, let's get to what a sampling distribution is. A sampling distribution of a statistic, so right, a statistic is any value that you can calculate from a sample. For example, the mean, the standard deviation, the maximum, the minimum, the median, the interquartile range, the range of the data, sort of maximum minus minimum. Any value that can calculate from the data is a statistic. In this case, we're going to care about the statistic, which is the mean. And so the sampling distribution that we're going to care about is the distribution of that statistic. Meaning, okay, I should also say, for a random sample of size n. Okay, so let's go back up to this diagram. So imagine the scenario where we've got this population, light blue. We draw a sample, which is the dark blue. From our sample, we calculate a statistic. Let's say we calculate the mean. So we calculate y bar. Then imagine we drew another sample. From that new sample, we calculate y bar. It'll probably be a slightly different value than the first y bar. Throw that sample back, draw a third sample, calculate y bar from there. Repeat that over and over and over again. If you do that, you'll get a distribution of what y bar is. And that is the sampling distribution of the statistic. Now, the standard error is the standard deviation of that sampling distribution. In particular, the standard deviation of the mean, SEM, is the standard deviation after that scenario that I just provided, where you calculate many y bars from many independent samples and you have this distribution. This is the standard deviation of that distribution. That's the standard error of the mean. And in the case of the mean, we have a nice formula. If you know the standard deviation of your population, or at least S here is an estimate from a single sample, then the standard deviation of the mean, or the standard error of the mean, is that sample standard deviation divided by the square root of n. That is, the mean is less variable than the population by this ratio, s divided by the square root of n. So as n gets larger, the standard error of the mean gets smaller. All right, we have two other definitions that we care about. There's the law of large numbers, which just states that as the sample size increases, that our sample mean, or any statistic, gets closer to the true value in the population. So our sample statistic gets closer to our population parameter as the sample size gets larger. All right. In other words, as more trials are performed, that's our sample size. So the more information you have, the better your estimate is. That's the bottom line. In fact, if your sample size was the size of the population, so that you conducted a census, then you would have, then your sample mean would be exactly your population parameter. Lastly, the central limit theorem is an important result that says that for certain statistics, that as your sample gets larger, that sampling distribution up here approaches a normal distribution. Okay, so if you have a sufficiently large number of samples, then the sampling distribution will be approximately normal. And this holds for the mean in particular, which is the main parameter or statistic that we care about. So the next sections illustrate the central limit theorem in action. So I'm going to jump over this code and these comments. Okay, this code right here is a function I wrote that basically illustrates the central limit theorem when you draw from a uniform distribution, where capital N is the number of samples to draw and little n is the size or number of observations in each sample. And I've got well-commented code here, so if you're someone who's really interested in coding and want to dig in to see what this does, you can learn what's happening there. So let's look at these 4 plots. The first plot includes samples of size 1, and the black histogram in the background, which is basically uniform, shows that sampling distribution when we've got 10,000 samples, but each sample only has 1 observation. That means that this is effectively an estimate of what the population looks like, because we're taking means of size 1. A mean of 1 observation is the same observation. So we have a uniform distribution here. The black line is a density estimate of the histogram, and it drops down at the bottom because there's no observations to the left of 0 or to the right of 1, and it's a kernel density estimate which basically averages neighboring values together in a certain way, and so it has this drop off. I wouldn't worry too much about that. Basically we have a horizontal distribution here. The red curve is a normal distribution where the mean and the standard deviation of that curve are estimated from our data. And what we're comparing is the central limits theorem says as the sample size increases, the sampling distribution of our statistic, of our mean, becomes more and more normal. So is that the case yet? Well, samples of size 1 look pretty bad. So let's increase this. N equals 2. This is now immediately looking better just by averaging 2 values. The black is actually a triangular distribution. You're averaging 2 values from a uniform distribution. That becomes a triangle distribution. But you can see some systematic deviances. You can see that the sampling distribution is overestimated on the left. That means it's higher than the normal distribution. And then it's lower in the middle, and then higher again on the right. It's those systematic distributions or systematic deviances from normality that we're going to worry about. And so this I would say isn't quite close enough for us to consider it to be normal. As the sample size gets to size 6, we still have small systematic differences, but not very big anymore. We're getting really close. And by the time you get to 12, except for this little hiccup in the middle, and I think if I were to draw another sample, you could actually try running the code again. You'll get something slightly different, probably. It looks really, really good. There's still tiny deviances. You can see the black line is a little bit above on the left and the right, and a little bit below in the center. But we're getting close enough that it's not starting to matter. Or, yeah. All right. Looking at a slightly more extreme example, this example's the same except it's from the exponential distribution. Exponential distribution has values that are close to 0 at high frequencies, and then they tail off as they get larger and larger, with rare events being very large, but still possible to be large. And so this is with 1 observation, means that are calculated from 1 observation. Here are means that are calculated from 6 observations, and you can see that the skewness from the original distribution, the black here, continues into the sampling distribution even at larger samples. So here we have sample size 6. We see some systematic differences from the normal. We have low, high, lower, and higher, and you can see a bit of right skewness. if I scroll down a little bit, here's a sample of size 30. Right, in our introductory statistics class, Stat 145 here at UNM, we learned that basically if you've got samples of size 30, that's good enough to use a normal approximation. Let's see, in this case we have systematically low, high, low, high. The black compared to the red is what I'm doing. And this is probably pretty good, but there's still a slight right skewness here. By the time you get to a sample of size 100, it's settled down a bit better. Though there's still small systematic differences, it's starting to get close enough to not worry too much about. So the main takeaway here is that when you start with a distribution that's fairly close to normal, you need a smaller sample size for the central limit theorem to effectively converge to a normal distribution. Whereas if you have a distribution that's quite far from the normal, it takes larger and larger sample sizes. Typically, symmetric distributions are going to converge quickly, whereas highly skewed distributions will take large sample sizes before they converge. And all this is important because the t-test procedures that we're going to learn in this chapter require normality of the sampling distribution. So we're going to use basically code that I wrote to look at these, what are going to be called bootstrap distributions. That's going to be an approximation of the sampling distribution to see whether the sampling distribution of the mean is close to normal or not. If it's pretty close, then we can feel confident that the inference from those procedures can be trusted. Whereas if the normal distribution does not appear to be met, for example, in this case up here with n equals 6 for the exponential distribution, this looks bad. And so I'm not going to trust a result from a t-test here. Instead, I would go to chapter 6 and look at a non-parametric strategy. A non-parametric strategy would not make a normality assumption. All right. A few other concepts to learn. The first here is a z-score. So what a z-score does is it subtracts the mean from your sample and it divides by the sample standard deviation. What this does is, regardless of what the distribution is of x, our random variable in this case, whatever that distribution is, it has a certain mean, x bar, and standard deviation, s. Well, if you subtract the mean and divide by s, if you do a location scale transformation, this z will have exactly the same shape as the distribution for x, except the mean will be equal to 0 and the standard deviation will be equal to 1. So this is another term for this is standardization. So this is a way to standardize the random variable. And in particular, if you have a normal distribution, say this one for IQs are centered at 100 with a standard deviation of 15. That's their definition. As we go through time and people get smarter because of culture and education and all that stuff, the IQ tests are recalibrated so that our current crop of people will always have an average IQ of 100 and standard deviation of 15. Well, if you subtract 100 and divide by 15, you'll end up with a distribution that's centered at 0 with a standard deviation of 1. And though there's many ways to do this, here is a normal distribution of size 100. I'm drawing a random, R is for a random sample from a normal distribution of size 100. I'm specifying the mean of 100, standard deviation of 15, and I'm putting that into a data frame which has a variable x in it. And then I'm scaling that variable and creating a new variable z, and the default of scale is to do the z transformation, subtract the mean and divide by the standard deviation. So if we look at a summary here, we can see that the mean of our sample of 100 was close to 100, and then after the z-score transformations, it's exactly 0. And the standard deviation has been has been set to 1 as well. So here is the same data. The first plot above is the normal distribution centered at 100, which is right about where my cursor is, and a standard deviation of 15. And below is now centered at 0 for the z variable, and a standard deviation of 1. Notice exactly the same shape. The only thing we've done is change the location and the scale of the horizontal axis for the data. All right. I'm going to let you read some information about the t-distribution. I'll say that the basic idea of a t-distribution is that it pretty much looks like a normal distribution, though you might not think this looks like a normal distribution, though these values were drawn from a normal distribution. So that bell curve, I'm paging up, this red curve here is a normal distribution. The basic idea of a t-distribution is it's a distribution that helps us estimate what the sampling distribution of the mean is when you don't know the variance of the population. Now, there's no reason why you would know the variance but not know the mean when you're estimating the mean, and so we will always effectively be in the situation where we will need to use the t-distribution for estimating the mean while we also estimate the variance. The t-distribution is basically wider than the normal distribution, and the width of it depends on the sample size. So it has a parameter called the degrees of freedom, which is 1 fewer than the sample size n. And so that if you took a sample of size 30, then our degrees of freedom would be 29. All right. And I'm going to plot several examples of a t-distribution. The red curve, which is the steepest, is a normal distribution. And as these centers go down, we have decreasing degrees of freedom. So the 100 is the top curve, and the degrees of freedom 1 is this bottom curve. That bottom curve has much wider tails. They're wider tails, thicker tails than the normal distribution. The normal distribution is actually quite steep. It decays off to 0 very quickly. By the time you're 3 standard deviations out, you've captured 99.7% of the probability density. There's very little beyond 3 or 4 standard deviations. Whereas with the t-distribution, even at 5 standard deviations out, there's still quite a bit more mass out there. And maybe an obvious point to say is that if your degrees of freedom go up to infinity, then the t-distribution becomes the normal distribution. All right. So confidence intervals you have learned in Stat 145, the prerequisite for this class. I will say that there are a certain set of steps that I'd like you to take each time that you, when you calculate a confidence interval and interpret it. And so my recommendation here is to first define the population parameter. For example, let mu, so this is going to be a definition of the population parameter both in words and in notation. So I'm going to say let mu, so that's our notation. Mu is for the population mean, equals the mean characteristic for the population of interest, meaning, if this was IQ, for example, that was an example we just saw, this would be the mean IQ for, college students age 18 to 24. That would maybe that's our population. Then we want to specify the confidence coefficient. So typically alpha is going to be 0.05, and therefore we're going to have a 95% confidence interval. Why do we use 0.05 and 95%? Convention going back to the 1920s when Ron Fisher decided that being wrong 1 out of 20 times wasn't so bad. And that has stuck so that no one really thinks about it anymore. But typically you would want to define this confidence coefficient to match the pain or the penalty of being wrong. If you're wrong about where the mean is, how disastrous is that for you? If it's really disastrous, increase this to 99%. You'll have a wider interval. If it's not so painful to get it wrong, then you can actually have a less confidence. Okay. Compute a t-critical value. That is, R is going to do all this for us, but typically this t coefficient is going to be somewhere around 2, or a little bit larger than 2, depending on what the sample size is, which defines the degrees of freedom. And then we calculate our confidence interval. Y bar is our best estimate of the population mean, and then we're going to add our uncertainty, which is the t value, which is around 2, and then the standard error of our mean. And we know the standard error of the mean is our sample standard deviation divided by the square root of our sample size. That is our confidence interval. And I always put this last, but I always want you to do it first, is to check the model assumptions. In particular, is the sampling distribution of our sample mean normal, or close enough to normal to trust all of this hard work we just did with the confidence interval. All right. No one gets the definition of confidence correct, and so you need to really know this. And I'm going to show you an example of this in a second. Confidence, I'll tell you what confidence isn't. Confidence is not probability. You will want to interpret confidence in this way, but this will be wrong. You'll want to say, we're 95% sure that the mean is between the lower bound and the upper bound, that the true mean is in this interval, but that is incorrect. The thing that is random is the sample. So you've drawn a random sample. Remember the picture way above? You've drawn a random sample, and once you observe your sample, all your calculations from that point forward are fixed. They're determined. So if you calculate a confidence interval, the confidence interval is based on this sample. If you were to draw a different sample, you would get a different confidence interval. Therefore, the definition of confidence is actually, if you repeatedly sampled the population and construct a confidence interval for each of your samples, then 95% of those intervals will be correct, meaning they will contain the true population mu. And 5% of the time, you will be wrong. Will you know it when you're wrong? No. I'm sorry that you won't know. So let me just show you an example. All right, so I'm going to zoom out a little bit. All right, there's no perfect way to put this on here. So I'm going to draw 100 samples. Those 100 samples are on this vertical axis, goes from 0 to 100. On the horizontal axis, the true population mean equals 10. And I have drawn for each sample, so this bottom one, the mean is almost 11, and the confidence interval goes from just below 10 to almost 12. And that interval contains the true value, 10. So in that case, I got it right. I know it in this case because I know what the population mean is, because I simulated this example. But in actuality, I wouldn't know. This is 9.9 up to 11.8 or something. And that's sort of my best guess for where the population mean is. And I'm either right or I'm wrong. And I'm right with 95% chance. And I'm wrong with 5% chance. And that's what that looks like. All right. So as I scroll up through all these many intervals, some of these indicate that I got it wrong. So these blue ones, you can see the left bound is greater than the true mean. So I got that one wrong, I got this one wrong, I got this one wrong, this one. And the pink one here, notice the upper bound is greater or less than 10. So I got that one wrong as well. And if I scroll up, I actually, exactly 5 of the 100 are wrong. So that's the 95% confidence interval. Now there's no guarantee that I would get 5 out of 100. That just happened to work out this way. But it's the most likely value. Sometimes if you rerun this code, you can try it. Sometimes you'll get 4 wrong, sometimes you'll get 8 wrong, and that's just due to the random sampling. All right. All right. So the assumptions are that so I've got what is often given as the assumptions for these tests, but I'm going to give you slightly less stringent assumptions in a second so that you can perform this test even when this is not met. So what they'll tell you in the intro stat is that your population distribution should be approximately normal. And you can check that by plotting the data and so on. What we actually care about is whether the sampling distribution of the mean is normal. And what we learned earlier was that even when the population is not normal, for example in the uniform distribution or the exponential distribution, the sampling distribution, if your sample size is large enough, the sampling distribution will be approximately normal by the central limit theorem. So that means even when we've got wildly shaped population distributions, we can still use the t procedure, the t distribution, to calculate confidence intervals and do hypothesis tests because the sampling distribution is roughly normal. All right, and we're going to assess that normality assumption of the sampling distribution of the mean with the bootstrap. And I'm not going to really talk too much about the bootstrap except to say that it is a strategy for treating the sample sort of like a population and doing all that resampling the way that we wish we could. Okay, let me scroll up to the top. That beeping is my cats at my front door asking to come inside. So what we wish we could do to calculate the sampling distribution of the mean is to draw a sample from the population, calculate the mean, and then draw another sample, calculate its mean, draw a third sample, fourth sample, and do that an infinite number of times. And if you did that, you'd get a perfect approximation of the sampling distribution of the mean. Instead, we just have a single sample. And if that sample is representative of the population, then we can use that sample basically as a version or an approximation of the population, and then we can sample repeatedly from the sample and calculate a mean each time, and then use that as a bootstrap approximation to the mean. And so that is what the code that I've written here does. For a one sample case, it calculates the sampling distribution using the bootstrap. That's how I've named this function. And the function is pretty well commented if you want to learn how this works. But the basic idea is, let me page back up for a second, is that I'm going to put in I'm going to put in the data set that I'm trying to estimate the sampling distribution from, and it's going to run this 10,000 times and see how close the sampling distribution of the mean is to a normal distribution. So here's an example I've got from another distribution now, a gamma distribution. A gamma distribution is sort of like a normal distribution, but it's skewed to the right. An exponential distribution is actually a special case of gamma. And I'm going to draw a random sample of size 10. And then I'm going to use the function I just wrote to test how close that sampling distribution is to a normal distribution. So I'm going to zoom out just a little bit. And the function produces these two plots. On the top, it's a picture of the original sample. So there's 10 observations here. There's 10 little tick marks, the rug just sticking up out of the axis down here. From there, we've got a histogram with the boxes and then a smooth density curve. And you can see this is a bit right skewed. And then below, I've drawn resamples from these 10 observations and calculated a mean of 10,000 different resamples. And that is the black histogram with the black density curve here. And the normal distribution is the red curve here. And we're asking, does that black curve look like the red curve? And it takes some practice to interpret this. Actually, we're going to be a bit sensitive and say that maybe this isn't quite normal yet. This black curve is a bit right skewed, and so I'm not quite sure yet that I would use this procedure on this data, though it probably won't be that incorrect. We mostly care about these tails. And so, for example, the 2.5% on the far right and the 2.5% on the far left, so that if we have the central section of 95%, and those two tails, you can see the black curve here sort of cuts off a little too quickly, whereas the black curve here trails off about right for the normal distribution. So we're going to have a little bit of a short tail on the left. That may not affect inference too much, but it's effective. We should be a little bit concerned in this particular case. If this assumption isn't met, we'll learn in Chapter 6 the ways of doing this analysis without the normality assumption using the non-parametric methods. All right, I'm going to pause the video here and come on back for a second part and start with this example of age at first heart transplant. And going forward, we'll do confidence intervals and we'll do some t-tests and wrap up the chapter.